Everyday products break or permanently deform when under too much load. This experiment aims to further understand why products and everyday materials break as well as running an analysis on the results obtained. The experiment involves using items found around us to conduct a simple stress-strain experiment.
The project was conducted using a bottle of water to bend a plastic spoon until the spoon breaks. First, tie a water bottle at the end of the shoelace, while the other end touch the plastic spoon. The spoon is then placed on the cloth rack. So, our group assumed 1 milliliter of water equal to 1 kilogram of mass. A measuring bottle was used to measure 100 milliliter before putting it in the water bottle. So the corresponding vertical deflection at the middle of the spoon was recorded. The steps repeat until the spoon fractured. What is elastic region behavior? So, elastic region is the initial phase of material deformation in a stress strain diagram where the deformation is temporary. Based on the results, material in the experiment shows an identifiable elastic region during the experiment. From the graph, the stress and strain both value increase proportionally from the start until the load reach 0.6 kg, as you can see in the graph above, indicating linear elastic behavior before entering the plastic region. By understanding the elastic behavior of the spoon, engineers can determine the durability and reliability of the product for mass production before selling it to the suppliers.
Young's modulus is the relationship between stress and strain in the elastic region of a material. And the higher Young's modulus means the material is stiff, and a small elastic deformation will happen when under an applied load. From our results, the Young's modulus obtained is 1.014 gigapascals, which when compared to other materials is quite low, considering another plastic, ABS plastic, has a Young's modulus of between 1.4 to 3.1, which is significant because even a difference of 0.1 gigapascals is the difference between a flexible plastic and a semi-rigid one. But this is expected from the result from the observation of our experiment.
What is the yield point? Yield point on a stress strain graph is the point where the plastic deformation begins. Even if the load is removed from the material, the deformation still occurs and does not return to its original state once the material reaches its yield point. So from the result, it showed that the plastic spoon has a low yield strength, which is a standard for usually thermoplastic product. Although the yield strength is low, the spoon can withstand the force that will be used for eating, making it suitable for intended use.
Assalamualaikum warahmatullahi wabarakatuh. My name is Amirul Hakim bin Muhammad Azan, matric number 230414. Alright, so for this part, I will explain the ultimate strength and failure behavior of the plastic spoon. Ultimate strength is defined by as the maximum stress a material can withstand before the failure occurs. It represents the peak point of the stress strain curve. During our experiment, after the plastic spoon exceeded its yield point, we observed that the deflection decreases significantly, while an increase in stress becomes less proportional. Sorry. This indicates that the material had entered the plastic region as the load continued to increase. The spoon eventually reached its ultimate strength and fractured. However, the failure did not occur suddenly. The spoon bent visibly and showed large deformation before breaking. This ductile failure behavior is typical of thermoplastic material and is beneficial because it provides warning before complete failure, reducing the risk of sudden breakage. Right, next I will discuss the toughness and resilience of the plastic spoon. Resilience refers to the ability of material to absorb energy within the elastic region and return to its original shape once the load is removed. So in our experiment, the spoon show limited resilience because it reached its yield point at relatively low stress level. However, the toughness refers to the total energy absorbed by material before fracture. Despite its low strength, the plastic spoon demonstrates relatively high toughness. This is because it underwent a large plastic deformation and absorbed a significant amount of energy before breaking. The gradual bending observed throughout the experiment indicates ductile behavior, which is preferable compared to brittle material that fails suddenly without warning.
Based on our analysis in designing the experiment, critical thinking skills were gained from conducting the experiment using commonplace items to fulfill our objective, such as the water bottle, shoelaces, and the towel rack. We also learned to work together as a team in experimenting. Oftentimes, figuring out the solution individually leads to clear flaws, but input from group members has greatly helped in finding better solutions and improving the experiment overall. Finally, the experiment has helped in understanding the topic involved greatly.
This experiment offered a simple hands-on approach to understanding the bending test of material if load applied. Even though the results from this experiment are acceptable, it is significantly different from modern material testing. In this experiment, force applied manually and observation to get the result totally were from the human. In contrast, modern method like universal testing machine can apply force at a control rate and can measure the deflection of the beams with high accuracy and precision. This modern machine can also calculate data such as flat shoulder strength, modulus of elasticity, and generate stress strain graph which can save time and money, and also has a lot of engineer in their research. In conclusion, modern testing technology can provide more accurate results than hands-on testing in evaluating mechanical performance in research contexts.
Right, for critical evaluation and material suitability for engineering application, this plastic spoon is low strength thermoplastic, designed by mainly for lightweight and disposable uses. So its flexibility and ductile behavior make it suitable for everyday consumer products such as disposable cutlery, where, saf- where safety, cost, and ease of manufacturing are important. But based on our experiment result, the material has low stiffness and low yield strength, which means it cannot withstand any height loads without permanent deformation. Therefore, the material is not suitable for structural or load-bearing engineering application. In engineering design that requires high strain, durability, and dimensional stability, stronger materials such as metals and reinforced polymers will be more appropriate, better than a plastic, actually.